The last part of the last lecture of this session would be given by Professor Charles Rosenblatt, and it's Nanoimaging of liquid crystals Part 2.
Okay, actually, you notice there's a slight change in the title. But doesn't really matter. Okay, so I want to talk about 4 different experiments that we've done using this technique of nanoimaging. And so again, if you remember this from the first talk, talking about the extrapolation of L, where we have the molecules along the pattern substrate over here, being uniform along the easy axis, here along the easy axis, but this is that extrapolation line. And the question is, can we actually see it? Can we make an image? People have measured this in the past, sort of indirectly. And our goal is to see if we can measure it directly. So what we do is we take our AFM fiber, we come into the liquid crystal, we scan, in this case actually somewhat higher level, about 70 nanometers, so we actually have to deconvolute our signal at the end because of this. And we scan it across here. And we do it in such a way that we start at one end of the cell, do a scan, and we continue to lower the temperature through the pneumatic toward the smectic A phase. So what we're able to do is for each line that we measure, we can associate that with a given temperature above the pneumatic smectic A transition and look at that extrapolation length now as a function of temperature. I don't think that Oleg this morning ever said what the extrapolation length is. I mean, he was asking for guesses, but I don't think he actually ever said. So typically that extrapolation length, it depends upon temperature, is of order a few hundred nanometers. So this is the image that we see. So we start over here, it's cold, it's warm, and as we come across back and forth, it gets colder and colder, and eventually we go into the smectic A phase in the liquid crystal HCD. And we're not interested in this, we're not interested in this, what we're interested in is this crossover region. And it's noisy, to be sure. We are not looking at huge signals. So if you come over here and look at the intensity, and these things have been shifted around a bit in order to separate the lines. But if you look at the intensity as a function of temperature now, you can see that at higher temperature you get this decrease. It's pretty fast. It does not occur over a very, very large distance. But as we cool down closer and closer to the smectic A phase, this length scale increases more and more. And this length scale over here will correspond approximately to 2L, because remember, we're going from this orientation to this orientation. And by the way, the intensity, the way we've set up the optics, it's such that the intensity is going to be linear in terms of the angular, the azimuthal angular variation across here. So if you look at the data over here, the solid lines represent the actual raw extrapolation, basically T over 2. But there is an instrument line. We have the fiber aperture, and that fiber is sitting a certain distance above the surface. So we have to deconvolute this in order to get the open circles, which would correspond effectively to the extrapolation length after we've done this deconvolution. So we look at the data. Again, it's noisy. In any of these things, you're not going to get beautiful straight lines where there's no scatter. There's a lot of scatter. We're looking at tiny, tiny intensities here. But what we wanted to do is compare this to results that were published many years ago by Bergenau-Litzter group at MIT. They did X-ray measurements of the smectic correlation length. Now, again, what we're looking at here is L. K33 is the bend elastic constant. W2 is the anchoring strength coefficient. The bend elastic constant diverges. It has a constant and then a diverging part because of the growing correlation length on approaching the smectic A phase transition in pneumatic. And you can model this with a 4-parameter, of course 4 parameters is a huge number of parameters for data that look like this. But nevertheless, the transition temperature we can get very, very well. And so what we're after is this critical exponent for the correlation length, which is related to K33. We're assuming that W2 doesn't have any critical behavior. And so what we end up with is a correlation length of 0.65, huge error bars here, clearly not as precise as what you would get with X-rays, but again, the numbers are effectively in the same ballpark, although we have large error bars. So the idea here is to see if we can actually see this extrapolation length, as opposed to doing things indirectly. And what we've done here is to see the extrapolation length and measure this as a function of temperature. Okay, number 2. Okay, surface-induced orientation order in the isotropic phase. This is an old problem. If you treat a substrate, either by doing UV illumination, or by rubbing the polymer, or by even looking at a homeotropic surface, and then you put a liquid crystal in the bulk isotropic phase on top of this, that surface is going to induce orientation order in the nearby liquid crystal, which will then fall off as you go into bulk. And we're going to work here right now with a scaled order parameter, S, and I assume that order parameters have been covered, everybody knows what this is. And so in the past, and in the past goes back 35 years now, it's been assumed that there's an interaction potential between the liquid crystal and the surface in a mean field type fashion that looks like the order parameter of the liquid crystal is proportional to some background constant. And this is important, that it's a delta function right at the surface. And there's no interaction of the longer ranges. If you plug this into Myers-Soutby form and carry it out only to the leading terms, and yesterday Left Long spoke about Myers-Soutby, you end up getting an order parameter at the surface, that's S naught, which is proportional to 1 over T minus T star. T star is the supercooling limit of the isotropic phase, and typically you can get within about 1 Kelvin of T star. That's pretty common. There should be a pneumatic correlation line, so you should actually see the order falling off exponentially with this length scale here, which is typically 10, 20 nanometers, something like that. Okay, just as an aside, if you include higher order terms in the Landau expansion, there's some new and interesting physics that occurs. There's a lot of theory that was done in 1982 by Ping Sheng. He predicted capillary condensation, pre-wetting transitions. People have looked at these effects when you have these higher order terms that are important when the order at the surface is large. But we're going to work in the small order regime at the surface to sort of throw away throw away the fourth order term, the cubic term, and let's keep things simple here and just look at this exponential decay. Tim Slukin and Panavirsky had done some work in the late 80s where they had a different potentially included a de-wetting term that gives you some new physics. But again, all of these have a potential that's localized right at the surface as a delta function. And this cannot account for instance, repulsions between a soft pneumatic isotropic interface and the substrate. Okay, so in terms of what's been done with experiments, sort of the granddaddy of the experiments was done by Ken Miano, where he took a cell, filled it with an isotropic liquid crystal, treated the two surfaces, brought a laser through and just measured the integrated birefringence, the birefringence that would occur at the two surfaces, and the bulk would give you no contribution at all because the order parameter is 0. He did this as a function of temperature and saw these results. Then there was some results later on by Ron Shen's group at Berkeley. He did second harmonic generation evanescent wave ellipsometry. There were very nice results, but the problem is all the results required a specific model. They had gross data, which often happens. There's a theoretical model, which may or may not be correct. And then they analyze the results in terms of this theoretical model. I shouldn't say not correct, but it may not include all the important ingredients. Okay? So it may be a partially correct model. So this has been the case with surface behavior in just about all things except for some very nice work done by Mushevich and Kosovar and Ljubljana, where they sort of looked at layer by layer behavior, bringing in AFM and looking at, say, force measurements in a smectic phase. That was model independent with very, very nice data, but it did not talk about what would happen in the isotropic phase. So the goal here is for us to use our MSOM and see if we can extract the order parameter as a function of height above this treated surface without having to resort to any models. So again, a cartoon is we have a surface that's treated for alignment, planar alignment. The isotropic is bulk. The bulk is isotropic. And close to the surface, we're going to get some surface-induced order. We want to measure this length scale of order. So we bring our optical fiber in to the bottom and we back it out slowly, 1 nanometer at a time, and look at, again, the integrated birefringence from the fiber to the substrate. And the conventional wisdom is you should have a decaying exponential with some characteristic correlation length that will depend upon temperature. So this is what our data look like. If we're sitting high above the Ni transition temperature, by high I mean only 2 degrees, you can see that there's a signal near the surface, but it's relatively, it flattens out very, very quickly as a function of height above the surface. But as we lower the temperature, and here we're only 50 millikelvin above the transition, you can see that number one, you get this flattening out further out, basically at a higher position. And number two, that there's a much bigger difference between the value of the intensity right at the surface and the value that you have when you go effectively out to what amounts to infinity, far away from the substrate. So we need to go back and take this intensity data and normalize it. We do this by going through effectively a cell with a laser in the same way that Miano did. This allows us to measure the total integrated birefringence through the cell, from which we can get a proportionality constant between, in terms of alpha for this height minus this height over here, basically the total difference as you bring the optical fiber out. So we can convert this intensity to a retardation. But a retardation, remember, is the integral of the birefringence. And the birefringence for a given material that we're using is proportional to the order parameter. So if the order parameter is saturated at 1, we're going to have, as a given birefringence, if the order parameter is 0, we're going to have 0 birefringence. But this is a constant that depends upon the material. So effectively what we have is a retardation that we measure as a function of height of the fiber above the surface, which is equal to this integral of the order parameter, where c is a known constant, lambda is the wavelength of light that's known. What we want to do is invert this. We want to obtain the order parameter as a function of height. So we just have to invert this, which means that the order parameter is going to be equal to a derivative of the retardation that we measure as a function of height. And notice where this retardation effectively flattens out well above, so we have 0 order in the bulk. That's exactly what we expect in the isotropic phase. In order to do this, you know that trying to take derivatives of data will give you a lot of noise. Okay, you can sort of have to do a fit of the data and then take a derivative of that. Taking derivatives of moderately noisy data is a very difficult task to accomplish. So we did a 3rd-degree Bezier fit to this, and we're working with that. And this are the results at different temperatures for the total retardation. And so this is what we get when we take the derivative of those Bezier plots, and we look at what amounts to the orientational order parameter as a function of height above the surface for a surface that's been treated in a certain way to give us planar alignment. First thing to notice is that the order at the surface is relatively weak. The order parameter stays roughly below 0.12. If you look at a bulk pneumatic isotropic phase transition, there's a jump in the order parameter, typically of about 0.35, plus or minus 0.05, something like that. So we're well below the order that you see in a bulk pneumatic phase, which means that it's valid for us to have thrown away those higher order terms. That's number one. Number two, if you plot the induced order at the surface, plot the inverse induced order as a function of temperature, again it's noisy, but you notice it gives us something that looks very mean field-like, which is to be expected. And also, this is as close as we can get to the transition. We effectively have an extrapolation between the first order phase transition and the supercooling limit of about 700–800 millikelvin. So again, that's pretty much what one would expect. There's one other thing I'll show you, but before that, notice the main feature though, and that's the thing that caught our attention, is that we are not seeing a decaying exponential. There is a shoulder there. Okay, the third thing is, what's some characteristic correlation length? Now this was not an easy measurement to make. It was done many years ago by light scattering to look at fluctuations in the isotropic phase near the pneumatic transition, and correlation lengths were typically of order 15 to 25 nanometers. It went up a little bit. The correlation length got longer as you got closer to the pneumatic phase transition. Sorry, losing my train of thought here. Correlation length, phase transition. Yeah, and because it's a first order phase transition, you do not get a divergent correlation length. But if you look at our data, this is our retardation as a function of height of the fiber aperture. This is relatively close to the transitions, somewhat further away. We can see where we're getting this bending over, and again, the numbers are pretty much right on target and doing qualitatively what's supposed to be happening. But it's that shoulder that threw us. Now, there was a question earlier about what does the fiber do? So it turns out that the fiber boundary condition tends to be that the order parameter derivative of the fiber has to vanish. Otherwise, there would be a generalized torque at the surface, which is something that we don't want to deal with. And so we took this boundary condition, went back to Ping-Sheng's calculations, and redid them by adding in this additional boundary condition. And it didn't change things very much. I mean, there's sort of a 10% change in the order parameter profile. And he's still not getting, with that delta function potential, he's still not getting anything other than an exponential-like decay. There's no shoulder going on. So it turns out that we don't think the fiber has any significant effect. So what we've been able to do is show, number one, that the conventional wisdom for the 30 preceding years just isn't right, because this does not require any fitting parameters. This is a parameterless set of data. It doesn't require any models or any special parameters. The other thing is that some people have thought about this. There was some work done by Elena Pikina in Moscow, recently some theoretical work, where she suggested that this shoulder here is due to a difference in surface tension between the pneumatic and isotropic phase. So where you have that sort of interface, which is a bit washed out here, that's going to give you a repulsion between the pneumatic isotropic interface and the surface, pushing the NI interface out, where the NI interface would be something like around here, basically where the shoulder is beginning to fall off. We originally had chalked this up to not localized interactions, but longer range potentials, but when we worked with numbers, we just couldn't get our numbers to fit. So right now, Pikina's model seems to be the best, but we're still not quite sure. Okay, next. Can we examine the pneumatic director in 3 dimensions? So we've done sort of a one-dimensional variation here. Can we do it in 3 dimensions? The short answer will be not as well as we'd like, so we're sort of getting started. So what we did here was to describe a herringbone pattern where we had 4 different types of regions. One where we had very hard rubbing of large force, one where we had softer rubbing, and then for each of these we had line spacings that were either 100 nanometers apart or 200 nanometers apart. We then put a liquid crystal down on the surface, and this is the region of interest where it's undergoing this sort of bend, and this is what we measured as a function of height. So here are the images. We actually measured these at 17 different heights, but here are the images that we saw. So with 100 nanometer, we saw a crossover in intensity. We again set the polarization so that the intensity across here would vary linearly with the angle. So with 100 nanometers, we did not see much resolution here, but what's kind of interesting is we saw quite a bit of fingering, even out to, it's hard to see here, but you can actually see fingering out to almost 500 nanometers above the surface when we had 200 nanometer line spacings. That I want to talk a little bit about. It gives us some indication of the resolution there. So I'm blowing this up over here. You can see this blow up. Now, the way we actually created this rubbing is not to rub like this, lift the tip, come back. We actually went back and forth. We did sort of anti-parallel scribing. And it turns out that pushing and pulling are not the same thing. You know, if you run a plow in the wrong direction, it's going to give you something very different than doing the plow correctly. And so as a result, if we look at the 200 nanometer spacing of lines, that actually corresponds to a 400 nanometer period from pulling here to pulling over here. And so we went back and looked at that section with AFM, and we were able to get an AFM image that looks like this, where we see a topography, so it's relatively large plowing, of about 18 nanometers peak to peak. That's an important number that we'll come back to. Okay, so we make images here. This is an image, say, at 115 nanometers. So the close line spacings, forget, there's nothing interesting that we can see, but the far away line spacings, you notice that we can measure intensity variation, periodic intensity variation across here. So we look at the intensity variation as a function of position. And you notice over here it goes up and down, as you might expect. Regions of maximum intensity correspond to a trough, a minimum in the surface topography. Why? Because we fill the trough with liquid crystal. So by having our fibers sitting above this, we are actually going through more liquid crystal than as if we were at a peak. Okay, so the minima in intensity correspond to the peaks in topography. These corresponds to the trough in the topography. So we can do some quantitative studies. We can sort of look at a typical average intensity maximum and an average intensity minimum, and we can create, this is a different art than I used in the first paper, but we can create this dimensionless quantity, Imax minus Imin over the sum of the intensities. It's effectively a reduced intensity difference. And we can do this here, we can do it here, we can do it for all of our data points done at many, many different heights. And so we plot that out, and it kind of makes sense when we're far above the surface over here. So if I have like an 18 nanometer topography here, and I'm looking at it from way up there, you're not going to see much of an intensity difference. But if I'm standing very close, that is down here, that intensity variation is going to look a lot larger. So the data points over here correspond to our intensity. And again, we can come back and use this very, very simplistic plane wave approximation, because that's effectively what we're measuring here, where we've expected intensity that has this form. The retardation, we know all of these parameters, delta n, we know the height of the fiber, the average height of the fiber. The one thing we don't know is delta z. That's what we want to get. Delta z would be the peak-to-peak amplitude of topography. And so we end up doing a fit over here to this very simple form, and we find delta z is roughly 17 nanometers with an uncertainty of about 2 nanometers. So what we're able to do, number one, is get the lateral resolution, which we know is going to be about 100. We've since improved it to about 60 nanometers. The other thing that we can do here is we can measure the surface topography optically using this technique with about 2 nanometer resolution. If you compare this to an optical profilimeter that's now out on the market, a typical optical profilimeter, they can actually do, the profilimeters can do better resolution than 1 to 2 nanometers. but they cannot do that sort of resolution over very, very tiny areas. So we can get a lateral resolution down to around 60 nanometers. That's considerably better than at least the profilometers I know of can do right now. So this gives us some information about the resolution. So let's turn to the 3D imaging. This is what we set out to do. Not successfully completely, but we have some results here. What we wanted to do is look at this region again where we get this change in orientation is going to be effectively an extrapolation line. And you can imagine that as you go further and further above the surface, the director is going to become more uniform. It's going to uniformize, which, by the way, is a word that you'll find in the Oxford English Dictionary. Okay? It'll uniformize. And if you're far enough above, the director will be completely uniform. Okay, so we look at this over here, the director pattern over here as we go across. The idea is to come close to the surface, measure the image over here, get the director, bring our fiber up a little bit higher, look at the total retardation from the fiber at this height down to the bottom, and it turns out that that's going to be a convolution of basically what's happening down here, which we've already measured, and then come up. And then we do this iteratively, each time using the data from below in order to calculate what's happening at the next higher layer. The data are too noisy for that. You can see that the data are too noisy for that. This is hard rubbing, soft rubbing. Again, one of the things we were able to get out of this was for the different rubbing strengths. If you sort of look at this, we can get a rough value of the extrapolation length that we can see directly. But instead of trying to actually do this full calculation, which was the original goal, we've since improved things, but it still requires more work, is instead we went ahead and used continuum theory to calculate the director profile above the surface. And so this is very close, this is very close to the surface. This corresponds to the orientation. And over here, from black here to black there, that would correspond to twice the extrapolation length. And as you go higher and higher above the surface, represented now here by this, which is already 600 nanometers, it's basically the amplitude of the azimuthal or variations is falling off, and it's becoming more sinusoidal. And we did the calculation, compared it to the results, and in fact, with all the noise, I'm not going to talk about what's going on over here, but with all the noise, and we only have one fitting parameter, and that's the amplitude, it actually isn't bad. So this is something that still requires considerably more work, but when we finally get it, we should be able to do imaging with resolution of about 60 nanometers by 60 nanometers by 1 nanometer. Again, in something that is you are going to be invasive. So you have to work with this only in pneumatics. Let me talk about this quickly. We're running out of time. I'm running out of energy here. Orientational quench disorder. Okay, so we'll try to do this very, very quickly. This is a water that's frozen in. It does not vary over time. If you treat a surface, you can imagine that, we talked about an easy axis. The liquid crystal, that easy axis is going to have very, very small frozen in variations. If there's dust, or if you're rubbing, for instance, with a rubbing cloth, the cloth may not be coming like this. It may hit something at an angle, wobble a little bit. So you're going to get this frozen in disorder that exists around the easy axis, and it occurs in all sorts of systems. My colleague Maurizio Nobili measured this in Montpellier using a sort of a gross technique where he got some very interesting results in terms of measuring the correlation length. What we're trying to do is get this on much, much finer length scales. So again, we do this with the ensom fiber. We come into the surface. We have our polarization set so that we can measure the order. So variations from the easy axis will be linear in the intensity that we measure. And so the initial one that we made was about 1.5 years, 2 years ago. And this is a map that shows the deviation in radians from the easy axis orientation, the two-dimensional mapping. we can take this, we can come up with a histogram, and we found results that are similar to Nobley's in terms of the width of the angle. That is, you're going to get roughly 1 degree variation. But it turns out that his resolution was 300 to 400 nanometers. Our resolution is now something in the neighborhood of 60 nanometers. Can we do better? The other thing is he was looking through a 10 micron thick slide. We're coming down to within 50 or 60 nanometers of the surface. So this is the goal that we have here. We can take that, we can do a 2D Fourier transform, square. Basically, we can come up with a power spectrum. This is, it's highly pixelized, you can see, but we can come up with a characteristic correlation length of about 300 nanometers, which, by the way, is sort of the length scale of the probe that Nobley used. I don't want to talk down Nobley. This is a joint project, so we're basically working with him using his samples, trying to improve on this. So we have new results. That was my student, Joel. You saw the picture of him in Paris at the beginning. He returned. He's now working on this again. So this is recent data. We're taking it with smaller pixel sizes, actually smaller than the aperture. And we're now doing, instead of a 2D Fourier transform, we're doing a 1D Fourier transform and analyzing this over many, many lines because you do have this circular symmetry. We can again do the Fourier transform and obtain the power spectrum. If we do not remove the Q equals 0 and keep that in because you're still going to have some background DC, this is next to the last slide basically. We can obtain the mean of the square of the intensity, and we can obtain the square of the mean intensity. So anybody who's done things like light scattering or correlation function should recognize something like this. So knowing this difference, the difference between this height, and knowing this sort of scale, we can go back, since we know what the intensity should look like as a function of angle, go back and calculate a mean square deviation. It's a little bit wider than we had before, but I trust these results more than the last time because of some modifications we've made. So the idea is to try to map out correlation lengths, correlation functions, histograms, and so on of the surface order, relate this back to how surfaces are treated, and then look at other properties to see what effect this might have on those things. And with that, I'll say thank you. There are lots of things that can be done. These are people that have worked on various aspects of this project over the years. Lunchtime. Good.
Right. Questions? Comments? I guess everybody wants to go for that. Oh, there's a
So
question.
when you
Yes.
bring the tip of the optical fiber close to the surface, does the surface of the optical fiber have some effect to induce some...
It depends upon, the optical fiber does not seem to have a significant perturbative effect on the order parameter magnitude, but it does seem to affect the derivative, the spatial derivative of the order parameter. That's what we checked out with another calculation like Shank's. If you have a significant amount of order imposed by the surface, then then you have to worry about issues like capillary condensation, things like that. It seems not to be that important when you're dealing with weak orders. So again, there are a lot of things you can do with it, and maybe one of the take-home messages is that it's almost impossible to find a perfect probe that can be used for everything. There are different sorts of experiments and different materials, and you have to adjust your experimental technique accordingly. This is a miserable technique for symmetrics, but it's really good for isotropic mathematics.
I was curious if instead of the transmitted light, you could use luminescence, for example, or fluorescence from liquid crystal molecules like 5Cb when excited in UV, or these multi-photon processes.
In principle, it can be done. Maybe it's something we should talk about. I have not thought about it. But yeah, that's a very good idea. And you could even look at, for instance, I guess what would amount to aggregation or nanophase separation or other sorts of things when you have dopants there. That is a good idea. I really haven't thought about that, but it's another thing to be done.
Are there any further questions? Okay, if not, let's thank the speaker for